Okay, so I don't know till where it got recorded, but the last part I was just telling that this 10 power minus 14 is something that is different from, you might have used epsilon naught before. This component is epsilon naught, and this is epsilon r, relative permittivity. I'm putting 3.9 because almost always it will be silicon dioxide, but here please remember to put minus 14, okay, because we are in centimeter, not in meter. It will be 10 power minus 12 usually if it is in meter, but since it is in centimeter, this 10 power minus 14, and the reason is some other terms which are physical constants which will be given as part of the numerical will be in centimeters. So only if this is in centimeters, then they will get cancelled and your final answer will be in ampere, etc. Otherwise there will be a problem, okay, and that is why I'm just stressing to remember this number. You can store this in your calculator if you want. If you just want to store this 3.9, 8.85, 10 power minus 14, okay. Denominator, we just mentioned that also, that is the thickness of the oxide. What is the separation between the gate and the substrate? How much is that thickness? That is nothing but the thickness of this oxide, okay. And this also, it should be written in centimeter. Whatever they give it to you, they might give it to you in angstrom, they might give it to you in meters. Convert that to centimeters also. So this is the first term here, okay. The second term, V gate. Now the problem with V gate is, this is actually the voltage. Suppose I am having some voltage here in the channel, right? Now this differential, that is what is the difference between the gate voltage and the channel voltage in this region. So this is actually nothing but equal to C ox into Vg. The differential, that is what is the voltage difference between the parallel plate capacitors. It might vary because in this side the channel is having 0 volts if the source is at ground. In this side the channel is having 2 volts because the channel and the drain are touching each other on that side. So the drain is at 2 volts. Here also it is at 2 volts. So what is the amount of charge that is attracted on this side? That is given by gate voltage minus the channel voltage through the channel region, and now that will be varying. So that is not very easy for us to deal with. So what we will do is, I'll remove this part. We will make one simplifying assumption. Okay, so we will try to get rid of this channel, because the problem with the channel is it is somewhere deep inside and I don't have the electrical connection to the channel. I have electrical connection to the bottom, which is the substrate. That is not the channel. So I want to, if I want to get the current and I have this channel expression, in my expression have this channel, this thing, I will never be able to calculate it because I don't know the value of the channel voltage. So we will make one assumption. Assume approximately equal to drain voltage plus source voltage divided by 2. That is the average. On this side, if you see the channel, it will be exactly at Vs because this is touching the source side. If you see on this side, the channel voltage V channel will be exactly equal to Vd. Somewhere in between, okay, we will just make a simple assumption that it is the average of those two. Now, therefore, I can rewrite this. Therefore, VGC equal to okay, so Vg minus that thing. Now what I will do is I will So I've just done one thing. Minus Vs by 2 minus Vd by 2 is already there. I'm adding and subtracting minus Vs by 2. So minus Vs by 2 is subtracted here, minus Vs by 2 is added here. So what I can do with that is minus Vs by 2 minus Vs by 2. I can combine these together to minus Vs. So what will happen is, therefore VGC equal to Vg minus Vs. Okay, this is the first part, and the second part is minus 1 by 2 into, just rearrange the terms. Okay, you will get this expression. Now this has a very nice form which is equal to Vg minus Vs is nothing but our good old Vgs minus, similarly that will become Vds by 2, 1 by 2 into Vd minus Vs. So this is the final expression for the gate channel. Now this is very nice because this is in terms of our terminal voltages. Our transistor, the three terminals are gate, source, drain. So all those things I can measure. So once I measure it, I will be able to get all these numbers. So that is why this last expression is very nice. So this is the one we will use in this expression. So this is the first part of the derivation, which calculates the channel charge. Now for the second part, where we are applying dq by dt. Okay, so now I equal to dq by dt. This is the general expression. I'm going to approximate it by qc by t. Okay, now qc is the one that we just calculated. We have the expression for that. What is this suddenly? Where did this time come from? Where is time? Time has not been considered anywhere in any of these equations. Time, directly we cannot use it, but we have very simple expression for time, which is okay, distance divided by velocity. This is our general equation for time, and the simplest equation. Now distance, okay, in this diagram current is flowing. For current flow, it is between the source and the drain terminals. It doesn't flow in any other direction. So what is the distance between the source and the drain terminals? It is nothing but capital L, which is the length of the transistor. The charges have to flow from this side to this side or this side to this side, but in either case the distance they travel is L, and suddenly some drain source velocity. What is this drain source velocity? We have not seen this anywhere before, and we will not work with velocity also because it's a very physical quantity. We don't know how to calculate velocity from electrical, but we can convert it, and the way to convert it is, since electric field, okay, is oh sorry, not electric field, this is one step ahead. Before that, the Vds expression, one expression for Vds velocity, again this is from maybe 12th standard physics. Drift velocity or Vds is given by this is not voltage Vds, okay, that is why I have written small v. Capital V, that is the drain source voltage. Right now this L by V, this small v, is the drift velocity of the charges between the source and the drain terminals. So one more expression to remember as part of this derivation is drift velocity is given by mobility into electric field, and this will try to take us away from all these physical parameters into the electrical parameters. So this again I can okay. This is where the electric field in the horizontal direction, that is drain source direction, comes into the picture. The drain source direction is where the charges are moving. If they have to move from source to drain, it is because of the force of this electric field. So that is where ds comes into the picture. And the electric field, that is what I just written. Electric field we can replace as the gradient of the potential, that is dVds. Now finally I am somewhere, I have my electric parameter voltage, and this I will again replace with mu into, instead of this derivative and all, I'll just replace it by the gradient, which is Vds by dx. Dx is again the distance between the source and the drain, which is L. So now I am in a very nice position because almost everything, this will be given because this is a material property of silicon. Whenever electrons are moving in silicon, they will have some particular mobility. So this number I will know. This is my voltage. I know this because I am only applying this voltage. And L is again a very, very global parameter, size of the transistor. So that is also known. So almost everything is known in the right hand side. So then put it back in here. So you will get, therefore I equal to, okay. So QC also we will replace. We had the expression for QC. It was something like C oxide into VGS minus VDS by 2. Okay, this was the expression for QC, the numerator, divided by T, L divided by VDS. So L divided by this term here, mu okay. So we'll write that maybe here. Okay, so C oxide, we had the expression W into L into epsilon ox divided by T oxide VGS minus VDS by 2. Okay, and up and down, whatever we can move, we will try to move that. So this L will come here to become L squared, right? Don't cancel it. So mu VDS will go on top. So mu into VDS will come here, divided by L, and L will get multiplied to give me L squared. Okay. Now I will erase this diagram. This is the final expression, but we will just rearrange the terms to put it into a more familiar form, where we will move all the physical parameters to the front part of the equation and the electrical parameters to the second part. So just move all the physical parameters. Mu is a physical parameter, you move it that side. W, L and all, whatever you can cancel, you cancel. Epsilon ox, P ox, we leave it there. V are all electrical parameters, you keep them to the right hand side. So therefore I will erase all this. Okay, so therefore I ds equal to, okay, now final expression, mu mu mu, epsilon ox, epsilon ox, T ox, T ox. Okay, this is one component into, now this middle part is super important for our design purposes. L square and L, one will get cancelled. So what I will have is one term which is supremely important term in digital design, and I'll tell you in 1 second why that is important. And of course, just finish off the equation with rest of the thing. VGS minus VDS by 2 into VDS. Okay, so VGS minus VDS by 2 into VDS. So this is the, sorry, there is one term I missed somewhere. This actually should be this whole thing where I derived it as VGS. It should be VGS VT. I completely forgot the VGS minus VT. Okay, so why this suddenly this VT came into the picture? I had done a mistake in the earlier part itself, where we were deriving that VGC, right? It was actually VGC minus VT to start off with. So the whole thing, we missed that VT, but please add that VT when you're doing it in the exam or something. So this is the final expression for the current, and this is the expression for NMOS current in linear mode. Why is this in linear mode? Because in all the derivations for the distance the electrons are traveling, we have assumed that they are traveling the L, that is the channel is existing from the source to the drain. What is the length of the channel? What is the distance the electrons are traveling, etc. Because the channel is existing from the source to the drain, okay, it means that this expression that we have derived is true for the linear mode of operation. Okay, so this is what I have written here. Now slight modification, like I said, we will not have to worry too much. It is a very easy conversion from linear to saturation. Okay, so what happens in saturation mode? For that, we just draw this diagram just to understand how we can convert this equation. Okay, so what happens in saturation mode? We already know the phenomenon. There is something called as pinch off, which means the channel doesn't exist till the drain region. Before the drain region itself, channel disappears. So this particular region, okay, is called the pinched off region. And as we keep increasing the VDS, right, as VDS increases, because now we are moving from linear into saturation region, okay, VDS is responsible for the horizontal electric field. All the excess VDS appears in the pinch off region, okay, that is some amount of VDS is responsible for moving the electrons, but beyond a certain point, okay, this pinch off point also slowly it will start moving towards the with increasing VDS, the pinch-off point starts slowly moving towards the source terminal. This is highly exaggerated, not by this much. But what happens is, as we keep increasing the VDS, right, the excess VDS appears only in the pinch-off region where there are no charge carriers. So the excess VDS is not responsible for the horizontal movement of the electrons. That is why in some ways this mode of operation is also called as a saturation mode. You can keep increasing the VDS, but the current is not going to increase. What is the component? So VDS, for example, you can divide it into the excess VDS, which is going to appear in this region. What is the actual component of the VDS that is responsible for this electric field? That is given by the boundary condition where VDS is equal to VGS minus VT. This is the part of VGS which is responsible for the horizontal movement. Okay, as we go above from linear into saturation, all that additional VDS is only appearing in the pinch-off point where there are no electrons. So the electrons have all been already attracted into the drained region. So that is why this is the boundary condition. So to go from this expression for linear into saturation, it's very simple. Wherever you have VDS, you will get the expression. So let us do that for this expression. Okay, VGS minus VT is here. Don't change it. VDS is here. Change that to VGS minus VT. So therefore, I'll remove this part. In saturation region, okay, IDS equal to mu Cox, those components stay the same, sorry, mu n into epsilon ox divided by Tox into W by L, okay, and the second part VGS minus VT minus VDS by 2, so replace that with VGS minus VT, so that is nothing but right VGS minus VT minus VGS minus VT by 2, so 1 minus half is half, and outside is having VDS in the end here, so replace that with VGS minus VT. Why we are replacing is this VGS minus VT is the amount that is responsible for the horizontal movement. The remaining component is only coming across the depletion region, or the pinched off region where there are no charge carriers. So that component does not contribute to the current. That is why the boundary condition, okay, where exactly pinch off occurs at this point, at this condition, VGS minus VT equal to VDS. Beyond that, okay, whatever VDS you apply, only VGS minus VT is responsible for the movement of the charges in the channel region. The remaining part of the VDS keeps applying across the region where pinch off has happened. It does not contribute much to the current. So that is why we don't change VDS anymore. We just fix it to VGS minus VT in this expression, and you will get the final expression for current, which is mu into W by L into VGS minus VT the whole squared by 2. So this is the final expression for current in the saturation region. Okay, so I will just summarize this in one table just so it is easy to remember. And now that we have finished it, I will also differentiate between NMOS and PMOS. So first, whatever we have derived, okay, Okay, and finally, so this is linear region, and this is saturation region. Okay, the condition is here, very easy. Okay, VGS minus VT greater than VDS. Like I said, to remember, when the drain source voltage is smaller, we are generally in the linear region of operation. When the drain source voltage is larger, okay, we are in the saturation region of operation. So we have two separate current equations also. Of course, this is the major part of the derivation. If you remember this expression, and remember that once we are in the saturation region, VDS can be replaced with VGS minus VT. In one step, you can come from this expression to this expression. So this last expression is the current in the saturation region of operation. So this is the overall summary of the NMOS current, and this is, again, we have made many approximations also, right? For example, VGC we assumed as VDS minus V plus VT by 2, etc. And many times we have made assumptions for the drift velocity, we have made assumptions for the electric field. So this is generally an expression that will be around 80 to 90%. So there are many commercial softwares which are called as circuit simulators. You will also be using this in a lab. When they use that, right, they don't use this expression. They might use a more complicated expression. They might have more accuracy, etc. But this expression, number one, it gives us around 80% of the answer. So one of the most important things that we learn in a class is not to try to equal a computer. That is, a computer might be able to give you the value of the current flowing through a MOS transistor much more accurately, right? But generally what we are doing here is to understand the qualitative nature. Now I have this expression, right? Now, like I said, the current calculation, the most important thing to see is how can we increase the current. We generally don't want to decrease the current, because that would mean we are reducing the speed, because current is directly proportional to speed. How can we increase the current? Now this is my expression, right? This is one expression, this is one expression. And the reason we want to observe this expression more closely is how can I increase the current? So we have many terms, and very simple, if I increase these terms, the current will increase. That is the natural solution, right? So let us look at each of these terms. Now the first part, this is the same in both mu, epsilon oxide, T oxide. We cannot increase any of these, okay? Because mu is a physical constant. That is, if I am at room temperature, I am working with silicon with a certain doping, the mobility of the carriers will be fixed. You cannot change it unless you change the material. Suddenly you say, suppose you are having a meeting with your teammates, and your manager is there and the speed is not enough, right? And very clever, you think, okay, the first thing that I'm seeing in this equation is mobility. Let's increase the mobility. What that would mean is you're changing the material constant itself, and you cannot obviously do that, right? Unless you're at a certain level where already you've had a Nobel Prize or two to your account, and then you're saying, okay, let's change the mobility, then they might listen to you. If you say, let's change the mobility in a general meeting as a fresher, obviously they'll all start laughing at you. So mobility is not something that you can change at all. Second component, epsilon oxide. Again, I said that epsilon oxide, you can even store it in your calculator, right? After many years of debate and research, finally they came up with one more material, which is hafnium dioxide. So that is also impossible for us to change overnight. We cannot have anything to do with that. T oxide. Now, T oxide, you might think, okay, let's make it a little thicker. Okay, we can change T oxide. But the problem with that is the technology, whenever you're working in a particular technology node, so for example, at the start of the design itself, much before we decide to calculate the current, much before that, the technology node will be decided. That is, for this particular design, this is our budget. So based on this budget, to get the best possible performance, we might work at 65 nanometer technology node. When something like that gets decided, automatically this TOX is also fixed, not possible to change. You can't keep increasing, decreasing. Fabrication doesn't work like that. So TOX is fixed when the technology is fixed. So that is also not possible to change. Then let us jump to the second part. Okay, these are all again very similar to T oxide, fixed with the technology. The VGS and VDS, even though we have different names for it, both of them are at power supply voltage or at 0. These are the only two values. And power supply voltage for 65 nanometer, no, everybody knows it's exactly 1.2 volts. Nobody changes that at all. So that 1.2, these two numbers also cannot be changed. Then VT. Again, there is not zero flexibility. There is some amount of flexibility in the threshold voltage. You can change it for some of the transistors to reduce it to a smaller value. People do that. Somewhere in the book, if you read, there is something called as process corners. So some amount of flexibility is there, but that is reserved only for the very senior engineers. As a junior engineer, okay, you're not allowed to touch that because this involves a lot of cost. Generally, when somebody makes, say, 1,000 transistors on the die, some transistors might have a different threshold voltage, specially manufactured for some very senior people, right? Because they want to work with ultra high speed circuits. So what is the highest speed you can give them? Give them a transistor with very low threshold voltage. I'll spend extra money in making that transistor for you because you're very senior and you know how to make good use of it. Here, take this extremely superb transistor. Let's give all the bad transistors to the juniors. Let them work with those transistors. So you're working with the bad transistors where the VT is also fixed. So you cannot change that also. So the only thing, literally almost all of VLSI, digital VLSI, analog VLSI design also for that matter, depends on W by L. This is the only thing that a digital designer, right, can change. He has almost complete. There is also upper and lower limits, but a lot of flexibility is there. So for example, in 180 nanometer technology, okay, L this is fixed. Nobody increases or decreases this. You can increase this, right? Look at this equation. This will become very clear. I mentioned somewhere in between, but now it's a better time to mention this. Suppose somebody is working in 180 nanometer technology, right? What is the meaning of that? That means that the transistor length is 180 nanometer. What that means is, at that point of time or in that particular technology, because of budget constraints or technological constraints, we are not able to make anything lesser than 180 nanometer. 180 nanometer is the smallest I can make. Now, nobody is stopping you from going from L equal to 180 to L equal to 360. Suppose you are working in 180 nanometer technology, it is possible to make a transistor with 360 nanometer length. Nobody will object. But look at these two equations, both of them. It could be in linear or it could be in saturation. Suppose you put 180 nanometer, you will get some value for current. Suppose you increase that to 360 nanometer, what will happen to the value of the current? Can you look at these two equations and guess? This is very important. If the value of the length is changed from 180 nanometer to 360 nanometer, which is a legal thing to do, you will be doing a very bad thing to the current. You will be making it half the value, and nobody wants to work with a lower current. Everybody wants to keep increasing the current to make their part of the circuit faster and faster. So if you are given 180 nanometer, you are getting a current of say 1 ampere. If you make that 360 nanometer, you will reduce it from 1 ampere to half ampere, which is a very, very bad thing. So that is why this is fixed. Nobody changes L in a circuit, okay? And if you're working in 180 nanometer, W min approximately 400 nanometer, W max 50 micrometer. So this is the range. Why W min is 400? We will see that it has something to do with the layout design rules. Why W max is 50? That is again because of the manufacturing capabilities. But you see that there is a huge, very, very wide range allowed here. That is, I can go all the way from 400 nanometer to 50 micrometer. These are all the values of W by L that are allowed for me. So that is the only flexibility that is allowed to digital and even analog. To a large extent, the only thing you can change in analog is maybe some of the supplies, like the current supply, the voltage supplies we can change. But other than that, at the transistor level, right, the only thing that you can change as an engineer, analog or digital engineer, what can you change in this transistor if somebody asks you? W by L. Nothing else can be changed because everything else depends on the technology. When the technology node gets fixed, that is why this technology node is very important. When the technology node is fixed, a lot of the other parameters like power supply, the oxide thickness, mobility, all these things will get automatically fixed. So that is why this equation is also very important. The only way in which we can increase the current, the only way in which we can make the circuit faster is by increasing. Again, W by L also is very important. W by L low means it is a slow circuit. W by L is large means it is a fast transistor which will in turn produce faster switching or faster circuit. So that relation is very important. This whole derivation, in my opinion, of course you might think this will come in the exam, I need to solve it. Of course that is correct, but the whole derivation is to show us that in the current expression, the only thing that is available for us as an engineer to increase or decrease the current is the W by L. Okay, so this is the expression for the current, and again this is in particular to NMOS. What about PMOS? So we will see the conditions also and then we will stop. Okay, so I will do it here only, and that is NMOS and PMOS, they are opposite to each other. Okay, NMOS is having electrons, PMOS is having holes. Just for that one simple reason, the whole properties of the regions, the current value, etc. changes. Fortunately, the expressions for the current are the same. Okay, so the only thing that is changing is the regions. So I will have to look at each condition, and this is the simple part. You make every condition upside down. So VGS greater than VT is off. This was for the NMOS. Switch it, make it opposite. Okay, VGS, if it is greater than VT, the PMOS transistor is off, IDS equal to 0. That is if the VGS, because for PMOS transistors, the threshold voltage is a negative value. It is already at minus 0.5 or minus 0.4. Now if your VGS is more positive than that, that is it is greater, for example even 0, right? It is not going to be attracting the holes and you are not going to have a channel current. So that is the first condition for on or off. So this is the condition for off. Okay, first it has to be on. What is the condition for on? VGS lesser than VT. Okay, and now we will look at this is still called as the linear region. Okay, So linear region, if I want, this condition also has to be reversed. If this condition is true, then the PMOS transistor is considered to be in the linear region. Equation fortunately stays the same. Don't have to change anything. Okay, linear region for both NMOS and PMOS. This is the single equation. For NMOS or PMOS, the linear region current equation does not change. The only condition, okay, the electrical conditions change for NMOS and PMOS. So same thing we will do here also. Saturation means that it is on, and in addition, VGS minus VT greater than VDS. The reason why suddenly in NMOS I said many times, if the value of the VDS is low, it is considered to be in linear. If the value of VDS is high, it is considered to be in saturation. Here why it becomes opposite is, here we are dealing with negative values. Okay, when we are dealing with negative values, because the source generally will be at power supply, so all the others will be lesser than that. So the smaller the value, it is in saturation. So it becomes opposite. The easy way to remember, first thing to remember is linear or saturation current condition, current equations are the same for NMOS and PMOS. Okay, the only difference is in the voltage conditions for linear and saturation. NMOS is in linear condition becomes PMOS saturation. NMOS saturation becomes PMOS linear. So the best thing is you remember the conditions accurately for the NMOS transistor. If the numerical has a PMOS transistor, you just invert the conditions. That is the best way to remember both set of conditions together. Okay. So this is this thing. Still so far we have not looked at the actual current. Let us look at a sample of what this looks if we plot it. That is, I'm talking about the actual graph for NMOS and PMOS. So okay, so okay, so this is a sample, and this is what the real curves look little different from this. We will see why, but this is a close to accurate curve. And first x-axis is drain source voltage VDS. Okay, and the dependent variable, that is based on this VDS, we can calculate the current, which is IDS, that is the y-axis. And I have drawn multiple, so this is a family of curves, it is not just one curve. And what is changing in each of these is VG. For example, I'm just writing some numbers, but what is changing is the gate voltage, plus the other thing is the gate voltage is continuously increasing. So what this means is, suppose you decided to work with power supply equal to 1 volt. This will be your VI characteristic. Suppose you decide to work with power supply 3.3 volts, then this will be your VI characteristic. Obviously, you will have two curves that are very different to each other. So based on your design, based on your requirement, you can see, okay, which power supply do I have to work with. Suppose the power supply is fixed, okay, then you have to change that W by L. Suppose you want this type of curve, with power supply equal to 1 volt, which means that you have to change the W by L by that much, because like I just said, even I just remembered that power supply is not in your hands. You have these characteristic curves for different values, but once the power supply is fixed to go from this point to this point, the W by L is the only option. So this is a family of curves for different values of VGS, number one. Second important thing, x-axis is VDS, right? And since this is an NMOS transistor, like I was saying, as your VDS increases, the NMOS transistor moves from linear region of operation to saturation region of operation. So I have drawn this dotted line, and there are two sides, this side and this side. Okay, can you tell me in this side whether NMOS is in linear or saturation? And obviously the other one will be true on the other side. So based on our discussion, on the left hand side and right hand side, which is linear, which is saturation? Okay, so the thing to remember, left hand side is basically measuring VDS. As VDS increases, okay, pinch off happens and transistor moves from linear to saturation, which means this side is my the transistor is in saturation region, and this side it is in linear region. And this dotted line, wherever it meets the VI characteristic, that is the boundary of linear to saturation. So also we can see that clearly as VDS increases, if you see the saturation region, it is a straight line. Okay, there is no change in the current value. If you see, for example, here, I can keep increasing VDS, current stays the same. Why does that happen? For that you have to see the current equation. In that current equation, VDS was not there at all. It was just VGS minus VT the whole square divided by 2. And that is why we see this sort of behavior, and that is why it is also called as saturation. That is, the current has saturated to a constant value. And the reason for that, actually, you know now, as we keep increasing the VDS, okay, all that excess VDS just keeps falling on the pinched off region where there are no carriers. Since there are no carriers in that region, it doesn't have a big effect on the overall current, and the overall current stays the same as we keep increasing VDS. So this is a sample VI characteristic for a NMOS transistor. PMOS transistor looks very similar. Okay, only thing is, instead of being in the first quadrant, everything happens for the PMOS transistor in the third quadrant. This is my VDS, this is IDS. If you want, you can write minus minus, and same thing. Okay, in the PMOS transistor, what this means is, what is the meaning of negative value for IDS? Very simple. It means that IDS actually flows from the source to the drain, because as we will see the circuits in the PMOS transistors, the source is generally at the highest possible level, that is at VDD, and all the other terminal voltages, they can be at most equal to or lesser than the source voltage of the PMOS transistor. So that is why everything happens in the third quadrant. VDS is also negative because it keeps increasing in the negative direction. That is, if VD equal to VS, it is at 0. As VD keeps reducing, the VDS magnitude keeps increasing, but becomes a larger negative number or smaller negative number. So that is why it is in the third quadrant. And the current also doesn't mean that the current is flowing in opposite direction or it's negative current. It only means that the current is flowing from the source terminal to the drain terminal, because whenever we plot I, we plot the generally we plot the current as the positive flow of charges. So here the current is flowing from the source terminal to the drain terminal, and here also we see for different curves as the gate voltage is reduced. That is, for -1 I might have 1. This might be minus 3.3 volts. This might be minus 1.0 volts. So as the gate voltage becomes smaller and smaller, I can get more current. That is the first thing. The second thing here, can you tell me which side is linear and which side is saturation for the PMOS transistor? Okay, so similar to that pattern, here also, as the VDS becomes more and more negative, it is in saturation. Okay, and VDS is less and less negative, it is in linear region of operation. So very similar curves, very similar behavior. Only thing is, in NMOS transistors, VDS is positive, IDS is positive. In PMOS transistors, VDS is negative, IDS is also negative. Never means that we're applying negative voltages anywhere. It just means that VD is lesser than VS. That is the only difference between these two devices. Okay. And the other thing to say is the linear and saturation. Generally, like we saw in the example also, because the gradient of the charges is higher in the saturation region, the current magnitude in both the cases, okay, the magnitude of a current for a given particular value of W by L, a particular value of gate voltage, a particular value of drain voltage, if you're operating it in linear region, you're going to have a lesser value of current. You're going to have maximum value of current if you operate the transistor in saturation region. So this is regarding the value of the current, and always remember two things. One is W by L. If the W by L is higher, we can control the current and get a higher value, and generally we always prefer
BL है, आधे BL है सही.